I'm gonna lie, it's just not the same anymore. Now I'm pissed off. Fuck. Now I'm fucking pissed off, and this is how we're starting the stream. Alright, fine. Then this is the way we start it, with anger. Just can't fucking go the way that I wanted it to. So here we are. Can you hear me now? Can you all hear me now? Is the mic on? Is it not muted this time? Because apparently I'm a straight rookie from the fucking depths of the dirt. I'm a worm. Nothing greater. Perhaps lesser. Perhaps I'm lesser than a worm. Perhaps I'm lesser than a worm. From the dirt we rose, into the dirt we go again. Right. But no, I was just I was starting a monologue, right, essentially on whether I'm making the right decisions day by day, right? I have desires and aspirations, right? But am I doing what is necessary to achieve this? I don't know. You know, recently I feel as though my internship, we'll say, is just wasting my potential. Every day I go in there and I do some very simple tasks that I try to complete with my utmost capabilities, with my complete competence. You know, I give 100% and I don't half-ass anything. So granted, I'm doing a good job. But I don't really see any purpose to this. The purpose is not defined. Although the purpose is a stepping stone, is it not? Although I'm not very okay with accepting that fact, you know. We all absolutely need the stepping stones. We all start somewhere. But I feel as though I should be beyond this stepping stone, and my portfolio would say otherwise, right? The things that I've done, like, put me somewhere in an environment where I can thrive and actually utilize my creativity and my knowledge. So, you know, eventually in time, hopefully, God willing, that is the outcome, and that the fruits of my labor will come to fruition will, you know, regardless, there's shit to be done, and I gotta do shit for whatever fucking reason. God willing. So I've been working on inductor circuits, RL circuits, right? We've transcended the RC circuits, so let's look at inductors. Alright, I'm gonna get into it. I'm gonna get into this bullshit, into this circuit theory. Perhaps you're interested in engineering or science in one way or another, or electronics in general. Then you're gonna learn a thing or two. You know, hopefully you're not a bum-ass idiot who doesn't want to learn anything, like low IQ. If you aren't that, and you want to learn something, and you want to increase your knowledge, amongst other things, your skill sets and stuff like this, then go ahead and stay right here and watch this dumbass stream. Alright. Alright, let's get into it. Let me get all my shit together, because I have nothing now. I have nothing in front of me. I don't even have my backpack in here. Backpack. Do I get more of a Diego or a Dora vibe? More of a Diego or a Dora vibe? What's the type? No, what's the boots? Bruh, boots. Are you fucking? That wasn't even one of my options, but yeah, you still had to jump out there, go out of your way to go ahead and disrespect me like that. Put some respect on my name with the boot shit. What is boots even good? Wait, did boots do anything beneficial? Like, the map is the map, right? What did boots do? He always caught Swiper. Isn't that what happened? Nah, I don't know. Swiper no swiping ass Alright. Okay. He's cute. Sure. Boots is probably working his chemistry station in the behind the scenes, probably working the chemistry station, cooking up some dope. You know what I mean? I feel like Boots gives me that kind of vibe. Like he's a real shady guy. He's cute, but it's a facade, right? He's a shady guy. All right, let me pull up my homeworks and stuff. Yeah, he's cute. And I got a latte. It'd be my final latte for this round. I have to get some more milk. Oh! It sure does bang, though. All right. Let me get logged in here. Let's switch over here. I can start drawing some stuff for you in the meantime. Let's see what I can draw. We're already here. Let's just get into it. Why is my computer so loud? The fan is working incredibly hard. Like, why? What is consuming all of my processing power right now? Are you kidding me? It's the stream? That's not typical. All right. I just recently had a test. I'm waiting to get the score on that back. I'm curious. Curious George, Boots, Andorra. Whoa. Oh, yeah. I missed a quiz. Oh. What's the comment? Crack. What's the comment? Blah, 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 blah. Whatever. Oh. Alright, modules. Bro, my PC is working so hard. 100. Yeah. Alright, I already did that one, so let's move on. That one was an interesting one. Let's do this, because this is a really interesting problem. Or, I don't know, or so I would think. Where's my pen? Here it is. Alright, so this is our circuit. Let me get rid of this. It's gonna annoy the shit out of me. Alright, let's see how the camera angle is, because I like to tilt it a bit. Oh, okay. Are you kidding me? Alright, give it a second. Give this primitive technology a second. Yeah, whatever. Okay. I'm gonna blow a gasket on that one. You know what I mean? Alright, we got this circuit here. We got an independent current source right here, and I drew it in the wrong direction, so let's just switch that around. It's like that. 10 amps, bang. Okay, and got a resistor here. Alright, we're gonna have a little switch going on. I don't know what's up with the geometry of the switch, but this is what it's looking like. Yep. Okay, I'm a circuit guy. Yeah, what's up with those flock cameras, right? You guys know what's going on here. Mass surveillance state. It's like we're approaching Orwellian government. Oh, Big Brother, Big Brother, please do not imprison me for no good reason. Please do not put regulations on me for me not abiding by the smallest law. Brother, please do not take away my rights and my freedoms. Please take away the flock cameras. Please get rid of the AI intervention within our daily lives. Please rid us of this overseeing, all-seeing eye that is controlled by that is controlled by humans, not a benevolent, loving, thing. It's quite scary, the flock cameras. It's a combination of the most advanced camera technology and artificial intelligence, right? So they surveil everything and they can catch all of the minute details. I seen a video also where another guy was pitching an idea to, I don't know who was listening to him, the camera was only on him himself, but pitching the idea that they should also put these cameras, perhaps not called flock cameras, but they should put these cameras on garbage trucks, because the garbage trucks do pass every single street. Yeah, I saw a vid on those. Yeah, I mean, it's kind of hard to miss. It's all the hype. But they want to put them on garbage trucks because the garbage trucks pass every single house on every street, right? They have to go everywhere. And so it'd be mass surveillance. And he was spewing the idea, this bullshit idea, that this would allow them to, monitor people's homes and their activities for, like, if we see a brand new washer, a brand new bathtub, tiles, a pile of tiles, these resources and materials utilized in renovation, then we conclude that these people are renovating. This now provides us the right to go. It provides, the right for us to go and ensure that they have a license, right? A license, or is that how he called it? Right, because some people like to do modifications on their home, but they don't have the license to do such things. I don't know. For me, in my opinion, it seems that it's just bad. Right? It's mass surveillance and it's an invasion of privacy. I don't know. I'm the type of person who tends to do most things myself. And now you're going to tell me I need a license in order to do a simple construction job? Yeah, just mass surveillance. Seems quite dystopian. Clusters of the flock cameras. I haven't been looking out for them myself around where I live. Saw a video that there are clusters of them around hardware stores. Oh no, I'm definitely going to pay more attention now. Yeah, just know that if you're out there, to detect location. Okay. Yeah, I'll have to look into that. Just know you're not alone, right? Seems that you're never alone. They know what you're doing. They know what you're up to. And the people who are in control of this technology are very oppressive. They want to control everything. They want to control the words that you can use. They want to control the topics that you can talk about. Not the kind of people that you would want in power. But yeah, here we are. Alright. So, t equals 0, we're originally connected to this portion of the circuit, right? It's like a switch, and then we're going to switch to this portion of the circuit, and we're going to be left with a little bit different topology. So, 20 millihenry, let's put down our variables. We're going to take all these into consideration, and now this is R. This is what we're solving for. So, it says find the value of R so that 50% of the initial energy stored in the 20 millihenry inductor is dissipated in R in 10 microseconds, right? So we're given these constraints. So 50% of the initial energy stored. All right, let's first determine that, right? So, all right, considering the steady state behavior of the inductor, or of an inductor in general, right? As t approaches infinity, which is meaning a long time, after a long time we've reached steady state conditions, We're no longer perceiving like conditions in the transient section where our current or our voltage is time dependent, right? We're beyond that. We've approached steady state. So as t approaches infinity, IL will equal, well, the inductor itself will essentially by the circuit be perceived as a short circuit. Okay, it's just a wire. It's just a wire after we've reached steady state conditions. So considering that, if we had a short circuit here, we modeled it as a short circuit. Let me just draw it out, right? So this would be essentially steady state conditions. Our circuit would look like this. Right? Okay, so it's just a short circuit, right? We just have a wire there to indicate the short. Okay. Put this, and we'll put a ground here too. I like to do that. So we'll do that. Okay, well, if that's the case, then by all means, our 10 amps is going to bypass this resistor because it's going to take the path of least resistance. So that means that as t approaches infinity, IL will equal 10 amps. It'll just equal the value of our independent current source, right? Because it's a short circuit, we're going to bypass the resistor. It has no effect on the current or the voltage. So considering that, we have IL equals 10 amps, but I'm going to write it in a different way. IL of 0, right? This is our initial current equals 10 amps because now we're going to, at t equals 0, the switch is going to flip to this side, and now we're going to do an analysis here. We're completely disconnected from this portion of the circuit, and our inductor is charged. Our inductor is charged. So now let's figure out how much energy has been stored in the inductor, okay? Because we want 50% of that to dissipate in the resistor within 10 microseconds, right? Okay, so that's the constraint. All right, so IL initial equals 10 amps. As we analyze this portion, t equals 0, we're going to flip to that portion of the circuit, and our new circuit's going to look like this. Oh yeah, and then we'll find the energy stored in just a moment. This is our new circuit now. After t equals, this is our new circuit, t greater than or equal to 0. Okay, right at 0 we flip, and any time beyond we're still connected to this portion of the circuit. Okay, let's find the energy stored in the capacitor right before we flip. Right before we flip. So it's gonna look like this. The energy, which we can call it the work, right? Work is a unit of joules, and energy is a unit of joules. So energy, work, it's synonymous. You following along? You paying attention? Comprende? Okay. No! That makes me think you don't know what's going on. Because very seldom do the cats know what's going on. They're just vibing. They're just a vibe. They don't know what's actually happening. They're just vibing. Okay. Anyways. Alright, so it's going to equal half times our inductance multiplied by our current squared. Okay, so this is the formula for the energy stored. And this energy is stored as a magnetic field if we're talking about an inductor. If we're talking about a capacitor, obviously the formula is different, but this energy is stored very well. This energy is stored in an electric field. Okay, so looking at this, we can go ahead and compute our value. Half multiplied by, we have 20 millihenry, which is 20 e to the negative 3, multiplied by our current of 10 amps. 10 amps squared. Okay, this is going to equal, let me pull out my handy dandy phone calculator because my other calculator's elsewhere, and I really wish I had it. Anyways. Turn that down. Can we see that now? It's a little too dark. Okay. So 0.5 times 20 e to the negative 3 times 10, 100. I'll just do it. 10 squared is 100. Bang. Okay, so we get 1 joule. All right, 1 joule. So half of, okay, so now we want half of this energy to be dissipated in the resistor. half a joule, half a joule. Okay. So now let's, okay, so logical analysis would say like, okay, what do we want to know now? We want to know what the current flowing through the resistor would be. So what is the current required to achieve half a joule, right? Because that's 50% of our current energy. Okay, so we're gonna plug back into that formula and solve for I, right? What is half of our current? Or what is not half of our current? What is the current required to dissipate half a joule? Okay, so 0.5 equals half. Again, 20 e to the negative 3, and then we're gonna solve for I squared. Okay. So we're just gonna get 1 divided by 20 e to the negative 3, 50. Okay, and then we're gonna say I equals the square root of 50 equals square root it. Where is it? There it is. 50. 7.071 amps. Okay, so that's the amps that is going to that is the current that's going to run through our resistor, right? And now we want that current. Let's see. Let's think. We want that current. What? That'll be our final current. Yeah. So essentially, looking at this circuit, if we want 7, it's just two elements in series, right? So they're both going to perceive the same current. And therefore that will be the current running through our resistor and also the current running through our inductor. So what that's going to look like now, if we write down the general formula for the inductor current with respect to time, it's going to look like this. IL of t as a function of time equals IL infinity plus IL initial minus IL infinity multiplied by e to the negative t divided by, we'll call it tau. And in this scenario, tau equals L over R, right? For an inductor, that's our time constant for an inductor. Okay, you can go ahead and derive that if you drew just a normal RL circuit. If you drew an RL circuit, then you can go ahead and derive that through, you're going to have a first order differential equation. And yada, 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 but I ain't going to go through all that. If you want to see that, then leave a comment. Dino, I'm not talking to you. I love you. Okay. All right, so we can go ahead and plug the numbers in here, and we're going to solve for R. So IL of t, though. IL of t. If it's going to go for a long time. Okay, so our infinity, IL of t, that's what we want to know. We want to know when IL is 7.071 amps, because that's going to be once we reach half of our energy. 7.0 amps equals IL infinity is going to be, if we're looking at just this circuit, we have a discharging inductor. Therefore, it's all of the energy will be dissipated as heat in the resistor. Therefore, we're going to reach a current of 0 eventually, right? We have no source here. So eventually all the energy will be dissipated as heat in the resistor. So this is going to go to 0 after a long time. Okay, so IL of infinity would be 0 plus IL of 0, which was that original 10 amps, minus 0, e to the negative. Okay, so now if we plugged in L over R here, we're just going to get R in the numerator. So we're going to say RT divided by L. Or we could have said TR, whatever the shit. Okay, so that's 7.071 amps equals 10 amps e to the negative. Yeah, okay, so we have all of these values. So we have R, and then R, what's our time? Our time was 10 microseconds. So 10 e to the negative 6 divided by 20 millihenry. So 20 e to the negative 3. 20 millihenry. Let me calculate that real quick, and then we'll get a constant there. 10 e to the negative 6 divided by 20 e to the negative 3. That's going to give us 5e to the negative 4. So 7.071. We can go ahead and divide that by 10 too. So we'll say 0.7071 equals e to the negative 5e to the negative 4r. Right, remember we're solving for the resistance that would abide by these constraints, essentially. Alright, so we can say that negative 5e to the negative 4 r equals natural log of 0.7071. And then we just say r equals negative natural log of 0.7071 divided by negative 5e to the negative 4 equals... Oh, shit. I only need one negative. I don't know why I did that. So, natural log of 0.7071 divided by, can you see that? Yeah. Divided by negative 5 e to the negative 4. 693.17 ohms. Okay. That's good. That's close enough to our answer. It's close enough. It's good. We'll call it good. All right, let's move on to the next one. So we're looking at this problem here. It's a little more complex of a circuit. It involves a dependent voltage source. I think we're going to require a Thevenin equivalent. Oh yeah, I should just go ahead and do that right away. That's right. All right, check this out. You peasants. Okay. There we go. That's the dependent source. Fuck. $15 ohms, 5 ohms, 10 ohms, 2 milliamps. Bang. Okay, do I got everything labeled? And then we'll do this. We'll say, yeah, t equals 0. That's going to close. And this is our I delta, which is determines our dependent current. I have something to say. Okay. Boots. Okay, so we have a independent current source. Again, steady state conditions, we're going to perceive the inductor as a short circuit after a long time. Therefore, if that was a short circuit, our current in the inductor after a long time will be the same as the current through the 15 ohm resistor. Therefore, we essentially just have a current divider here. All right, we have a current dividing circuit. So we'll use the current dividing formula, the current division, and that'll be our initial conditions. Okay, so that's going to look like 2 milliamps multiplied by 5 ohms divided by 15 plus 5, 20 ohms. Okay, and this is what IL of 0 equals. IL of 0, yeah, IL of 0, okay. And that equivalates to, let's see, 2e to the negative 3 multiplied by 5 divided by 20, which is 1/4, right? 5e to the negative 4, 2e to the negative 3, 5 divided by 25e equals 5e to the negative 4 amps. Okay, beautiful. So now that we did that, okay, now t equals 0, our switch is going to flip, and now we're connected to this portion of the circuit, which now I'm going to find the Thevenin equivalent, and we're going to assume the inductor is the load, disconnected, find the Thevenin equivalent perceived at the terminals, and this is going to simplify our analysis by magnitudes, by factors, far greater than you could even comprehend, far greater than you could perceive, right? You don't even know what's going on in the inner workings, behind the scenes, okay? You don't know what happens behind closed doors, okay? So our new circuit is going to look like this. I'll draw it out so we can better perceive it. Like that. Like that. And we have this independent current source. And this is our terminals A, B, 4 ohm, I delta, 4I delta, 1 milliamp. Okay. Well, you know, the thing about this is that there is no current flowing right here. Therefore, this dependent current source is probably just going to be an open circuit. Yeah. He's not going to play a role. He's not going to be pushing any current. That's for sure. So, right, there's no current here. Right, so I think that's just open. So what, our Thevenin equivalent? We don't want... I want a Norton equivalent, though. Oh, I want a Norton equivalent. Not a Thevenin equivalent. Okay, so let's do the Norton equivalent. So that means we're just going to perceive this as a short circuit at the terminals. That was really bad. My bad. That was a really bad drawing. So, I short. Okay, I short. Okay. Okay. So that's our I Norton. And what is that? So our I Norton is equivalent or equals I delta also. Okay. So looking at this, we have, and we could say those two and this guy, right? So this is, we'll call him I4. Okay, so I delta plus 4 I delta plus, I'm just using a KCL, right? Kirchhoff's current law. I'm looking at all of, this is essentially one node here. This whole thing is one node. So I'm looking at all of the currents entering or exiting this node, right? KCL. Okay, so I delta is entering, 4 I delta is entering, 1 milliamp is entering, equals I4 is exiting. So he's the only one who has a different sign. Okay, so if we go ahead and solve, what do I know? So I have two variables, two unknown variables. But only one equation. So we're going to need another equation. Never mind, because that resistor's not playing a role. That doesn't exist. 0, right? If we have a short circuit, we're just going to bypass the resistor. I mean, we're going to go to the path of least resistance, so... Get him out of here! You know what I'm saying? Okay, he's gone. So we can essentially get rid of him. I4 doesn't matter, non-existent. So now we just have these two and I delta. Okay, now we have one very unknown variable and we have one equation we can solve for it. So it's going to be 5 I delta equals negative 1 milliamp. I delta equals 1 milliamp divided by 5. Fuck, it's going to be like 0.2 milliamps? Yeah, that's what it'll be. Let's just double check. 1 e to the negative 3 divided by 5. Yeah, 2.2 milliamps. So negative 0.2 milliamps. Okay. All right, so that's our current. And then now let's find the, what? Yeah. Which also equals I Norton. Okay, so let's find our Norton equivalent resistance. And now we have a dependent voltage source, so in order to do this, we're going to assume a test voltage at the terminals, which we are looking at into, like our AB terminals, as right here. So our new circuit's going to look like this. In order to solve for this Norton equivalent resistance, it's going to look like a positive whoa, do we want to do that? Yeah, that's fine, right? Yeah, let's do that. 1 volt. And that's an independent current source is going to be an open circuit, right? Just an open circuit. The current's going to equal 0. What kind of element in a circuit does the current equal 0? It's an open circuit, right? It's just two terminals, no connection between them. All right, so that's going to look like that. And then we're going to have our dependent source here. Again, for I delta, 4 ohms. This is I delta. I delta also equals our test current. So, okay, 1 volt. All right, this is 1 volt. So the current through him, current through the 4 mile resistor, we'll just say I4, and I'll label it I4. I4 equals 1 volt divided by 4 ohms because they're in parallel, equals 0.25 amps. Yeah, 0.25 amps. This is for I delta. We can say I delta plus 4 I delta equals 0.25 amps. That's 5 I delta equals 0.25. 0.25 divided by 5. It'd just be 5.05. I delta equals 0.05 amps. Okay, so our Norton equivalent, can you see that? Our Norton equivalent is going to look like this. It's a current source, like that, and we're just, and then we have this resistance here, and we have our inductor, like this. And our, okay, we forgot a step. So now our Norton equals 1 volt divided by 0.05 amps. And what does that equal? 1 divided by 0.05. 20. That equals 20 ohms. 20 ohms. Okay, so 20 ohms. This again was negative 0.2 milliamps. Negative 0.2 milliamps. Okay. Sure. So after a long time, and this is what again? This is a 2 millihenry. Okay, so again, after steady state conditions, the inductor is going to look like a short circuit. We're going to bypass this capacitor. So IL infinity equals negative 0.2 milliamps. Okay. So now writing the general equation of T, equals, I forgot, what do I want to solve for? Am I solving for voltage? I am. Yeah, I'm solving for voltage. So we'll do that in just a second. We have a relationship, right? Okay, Dino. T equals infinity, negative 0.2 milliamps, plus initial, which is 5e to the negative 4 amps, minus negative 0.2 milliamps, multiplied by e to the negative, 20, divided by 2 millihenry, 2e to the negative 3, t. What is that value? 20 divided by 2e to the negative 3. Nah. Nope. I mean, I'm pretty sure. I'm pretty sure my answer is right. I'm pretty sure my answer is right, and that they're wrong. Because absolutely everything is correct. Okay. Well, all right. I don't know. We'll conclude. It's just the fact I'm getting e to the negative 10,000, and it's saying the answer is e to the negative 5,000. And the only way I could achieve that is if I got 10 ohms here, and it's just no. 0.25 divided by 5. Let's use AI to check. Bro, I don't want to ask AI shit. Fuck AI. Ah! All right, well here, let me see though. Let me conclude, and then sure I'll ask it. 0.2 plus what would that be? That'd be 0.5 plus, wait, 0.2, so 5 plus 2. Alright, isn't that it? 5e and -4, that'd be 2 plus 2. So it's gonna leave us with 7, so negative 0.2 milliamps plus 0.7 milliamps, e to the negative 10,000 t il t, and then VL of t equals L times the derivative of I with respect to time. So the derivative of this expression, this doesn't have a variable in it, so that's 0. It's a negative, so that's 0. Derivative of this would be negative 10,000. So VL of t equals, it would be negative 10,000 multiplied by 0.7 e to the negative 3, be negative 7. Solve this one, bitch. Solve it, bitch AI. Bitch AI. All right, thanks for joining me today. You all are so lovely. I really enjoy my time with you. Thank you for being here. Until next time, and I don't know, let me try to be more entertaining or something. I'm not really sure what I'm doing. Yeah, not really sure what I'm doing.